So I'm going to tell you about radio astro tools and spectral cube. This was started kind of from an ALMA perspective, so there's a little bit of a radio bias here. But what I'm going to tell you is that actually these tools are pretty generic and useful by everybody. This is the group that originally worked on this code. I gave a similar lightning talk last year at this same-ish conference. If you want to see the talk, it's there. It's going to have exactly the same outline and everything. So what has changed since then? There's a changelog here. You can see that. But the important thing is actually not much has changed. And that means that this is pretty stable code. So I'm going to tell you a little bit about what it does. But the only things we've done are minor enhancements and performance enhancements, basically. It's working pretty well and is ready to use in other applications. So if you go to the website, this is what the software tools for radio astronomy looks like. Spectral cube is the main thing here. So yeah, we're really trying to pitch this at radio astronomers to get them to start using some of the Python stack a little bit more. But this, of course, is also, Spectral cube at least is an AstroPy affiliate now. What Spectral cube does is file I/O, some manipulation of the cube, so like treating them as arrays. It can do things like flatten them, make projections out of your cubes, or extract spectra from them. And then it can export them back to FITs, following the standards very well compared to many other tools. It can also send whatever cubes you have to visualization tools and to other analysis tools, for example, to YT, to PV extractor, and to glue. So it has these ways to visualize the cube, so you don't have to worry about as much about what format your data are given you. You can send them off to other things. So this is just sort of the general workflow, and there's some nice examples, especially the visualization examples are cool using YT. It can also do the translations there between frequencies and losses. So these are just some examples. You can very easily open cubes. So the top one is actually showing how to open a cube in Casa. Second one is showing how you can change units. So if you want to go from frequency to velocity for your cube, it doesn't require changing anything about the underlying data. All it's doing is changing the spectral axis, so it's very cheap. But this was actually it took a lot to implement the FIT standard properly here. And taking chunks, if you want to get chunks of your cube in velocity space and frequency space and wavelength space, those are all done with AstroPy units. If you open a cube and you print it out, it gives you some information about it, so its size, the min and max along each axis, the unit, nice things like that. You can see all the various features that it has. There's this tab completion, and just highlighting some of the ones you might look at. You can apply functions across the cube, and these apply functions, the reason they exist as separate things is because you can sort of do things lazily with these cubes. You might not, if you have a cube that's arbitrarily large, like tens to hundreds of gigabytes, you can actually load that here. It's using NumPy memory mapping in the back end, so you can then map functions across that and do it without loading the entire cube into memory elements. Cool. There's the two functions in yellow there. Those are visualization tools and analysis tools. And the really interesting things maybe are in blue. There are various ways to get subcubes and subsets of the cubes so you can do your analysis on the part you're actually interested in. One example analysis tool is PV extractor, which allows you to make slices along a cube and extract a position velocity diagram, or just, it's not velocity necessarily, but that's usually what we're looking for. And so you can draw arbitrary paths, because Tom has written some really cool stuff for that. And then you can even average over some width around any given path, and out comes your position velocity diagram. I picked a particularly ugly example because I was making this. I want to change the color map from jet, which was there before, to now it's grayscale. So we fixed that problem. Well, there's a pull request out for it anyway. Glue can do this even better, and so Tom, I hope we'll talk about that more at some point. There's this Casa Python thing. Probably if you aren't using Casa, you don't need to worry about this, but if you have Casa on your computer, you can install the entire AstroPy stack into Casa thanks to this tool. Again, Tom deserves most of the credit here. And so for the rest of this meeting, these are the things that we want to do. We want to add a new visualization methods going to Ginga. We want to replace PyRegion with AstroPy regions, which we're making progress on already. And then I'd like to hear, what are the use cases you guys have, and get more people using Spectral Cube because it works efficiently as a backend for other things, I think. Great.
Awesome, thank you.
Are we allowed to?
There are no questions now, so find the person at lunch. This is like a computer time test.
I see.
So lovely.
I would say at this point, you just scroll through it.
Okay. But it's frozen.
Oh, is it completely frozen?
Yeah. So if someone wants to swap with me, and I
Yeah.
go.
Yeah, so I'm going to show you guys how to load data. This is specifically simulation data, but it turns out you can load data of any kind so long as it's volumetric into Minecraft. Most of the nitty-gritty details for how to actually do this were worked out by Robert Thompson, who's a postdoc with me at NCSA in the Data Exploration Lab. The code is at this Bitbucket repository. You can see here there's a README that shows you how to do all this stuff. So bitbucket.org, data-exp-lab, PyMinecraft. PyMinecraft itself was originally written to use Minecraft from the Raspberry Pi, and that was forked, and now people can communicate to Minecraft from Python. Here's a script that shows you how to take data. So we're taking data from YT. This is a cosmological ENSO data set, creating a surface at a fixed density threshold. And then we're also getting the temperature at that surface. And then converting the data into the surface is a bunch of triangles. We're just replacing the triangles with individual Minecraft blocks. Convert to blah, blah, blah. Talk to the Minecraft server, and then give the Minecraft server a bunch of blocks. It turns out these colors are like different colors of wool. So that you get this nice rainbow color map. So this is a huge hack. It involves using a modded version of Minecraft. You have to download packages from sketchy websites. So here's how you actually start it. Oops. So starting a Minecraft server, Spigot is a modded version of the Minecraft server. So that's started, and I've already loaded the world, and it's already preloaded. It takes a really long time to actually create the world. Then I actually have to start Minecraft and join the server. So I'm going to play as me. First rule of live demos, don't do live demos. So it's a multiplayer server. If somebody else is in here on this network, they could probably, they might be able to join it. Yeah, so that's it. I'm going to, so I changed the weather to clear, and then time, set day, so that makes it day now. This is a cosmological simulation. Fixed a density of 10 to the minus 30. You can see here where we screwed up mirroring it periodically, so you can see a little seam there. So yeah, you can fly through the cosmological simulation. The black blocks are where Minecraft is breaking and it's not drawing the textures correctly because we're loading so many blocks that it doesn't know what to do with it. Can you kill it? I can kill myself by falling through the world. Oh no, here we go. So, and then I can punch.
It explains why the NGM is so hard to find.
But yeah, that's it. Well, do I have anything else I wanted to say? Oh yeah, We also got it working with the Oculus Rift. So this is the director of NCSA, Ed Seidel, looking around at the last supercomputing conference. This was our demo for supercomputing. Yeah, that's the Minecraft soundtrack you hear in the background. That's it.
Okay, so it looks like we're going to move on to Pey Lian.
It's hard to follow up with that one. I don't have World of Warcraft or anything, so. But it's exciting. You're going to witness history here. It's the first time this spec which is my lightning talk, is going to be demo on a Windows machine. Okay, so quick. I'm not going to talk too much about this, but basically it's a result of the sprint, data analysis sprint for JWST that Eric Tollerud talked about. So this is one of the products that we have. As you can see, lots of people contributed. And the main developer here is Nicholas who's not here at the conference. Ivo put a lot of the modeling stuff into it. There are a lot of other people contributed here and there. I wrote the documentation mostly. So I don't have time to give credit to everyone. It's on GitHub, Space Telescope GitHub. It has a proper read the doc that you can get information from. So with that, let's go to the GUI. So it's a GUI to a simple visualization of 1D spectrum. So it's not to compete with Glue or other more sophisticated cube tools that you have seen so far. Here I have a spectra preloaded for speed, just for the speed of the talk. So if you use the mouse wheel, you can kind of just zoom in and out. And if you click left click and drag, you can kind of move it around. So it's pretty handy. Here's the region of interest. You can kind of drag this to expand this or move it around, slide it around. Here you can see the wavelength in angstrom, which is read from the file. On top, this is pixel right now, but you can change it to hertz or whatever. Here's the flux unit. So if you go to the context menu, there's a lot more things you can do there, but I don't have time to go into that. If you slide this around, you can kind of see that the number here changes the basic statistic. So quick look of your data. Let's hide this real quick. Oops, no, that's not how you hide it. Removed, okay. So let's do equivalent width real quick. So this is a prototype, okay? So here you have your feature, and the two green area is where you get the background. So a very quick and dirty calculation, you get equivalent width information here. So let's get back to our region of interest. So you can choose models. We use AstroPy modeling. So here for the speed of this talk, I preloaded a Gaussian and a constant. So they are going to make a compound model. And let's hope it not crash. Create layer. So now we have a model. Of course, I haven't fitted it yet. It looks pretty bad right now. So now I'm going to perform fit. All right, it's getting there. Fit again. Fit again. Oh, okay, good enough for me. So you can fine tune the parameter. Like the previous talk, it's important to have proper initialization sometimes. So you can go into here. This looks better on the Mac, by the way. I see lots of Mac users. So you can click on this, and then you can change the value to initialize it. And then you can go to update layer, and it will update the model for you. And then you can maybe fit again. You know, you can do a lot of stuff with this. So that's the point of this project right now. If you go to our GitHub issues, you can see there are a lot of issues. Oh, so slow. But to show you that we have plans to work on this some more. There's a future sprint session to come back to this and handle those issues. But if you want to solve the issues for us now, you're welcome to pull requests. 0 right now, but we welcome pull requests. And you can read the documentation. That's it.
Thanks for having come early in our
So thank you, Tom. So I will talk about Morphometrica and a little about galaxy morphology. So how can we measure galaxy structure and morphology? We have two main ways to do that. We can fit light profiles for subcomponents, or we can measure non-parametric parameters like concentrations, asymmetries, smoothness, how the galaxy is asymmetric, and go on. And we can measure that with Morphometrica. I will talk a little about that. Morphometrica is a standalone application. It's written in Python. It's designed to be used in data from large surveys. It's easy to run in parallel. It's going to be open in the near future. If you want to know more about it, check the address. So here is the visual output. It's really easy to use. You only need to have the physics image and the PSF, and it gives you all the parameters that you need to do this kind of studies. So, but what's new with Morphometrica? Morphometrica takes the usual parameters for non-parametric morphology and changes them a little bit. It takes the asymmetry and smoothness and uses a Spearman-Hank correlation coefficient to do that. Instead of using Gini coefficient, it uses the information entropy, and it has a new way of measuring structure. We call it spirality. We normalize the galaxy image to normalize the position angle. We take the image in polar coordinates, take the gradient field from the image, then take the standard deviation of this field, and you can see that spirality correlates very well with the t-type. And it's a way to measure structure, new way to measure structure. But how do we know that this approach is better than the usual one? So we measure these things in Redshift simulations using Ferengi. It's not in Python, unfortunately. It's in IDL. So here you can see the simulations for the Feg Catalog. Is from the STSS DRA, the data. And you can see that all the new parameters are better to discriminate morphological classes. S3 is the new one, A3 is the new one, information entropy for compared with the Gini one. So if we do feature selection with that, we can see that all the new parameters are better to discriminate classes, plus the concentration, usual concentration. So we use Morphometrica, Galaxy Zoo to label our data, and we use scikit-learn to do all the machine learning supervised classification, and we are able to achieve a performance of 90% in the classification for Effigy, Nair Abraham, and legacy data sets. So the important thing here is that these measurements have physical meaning. Usually people do supervised classification in hundreds of parameters and they don't have physical meaning. So we are able to reproduce human classification with these parameters. And the distance from the class separation hyperplane can be used as a morphology estimator. It correlates very well with the type. And where do you want to go with this? So we want to find the limiting headshift for reliable morphological classification. So we want to give an instrument know what's the limiting headshift to do morphological classification. So you see here in the previous classifications the relationship between our supervised classification and the t-type, and after, in this case, point 2, the score relation starts to break down. And we want to find a general limiting function of this kind. So here's the classification metrics, and that's it. If you want to talk to me about that, I am available during the conference. Thank you.
Thank you.
Thank you, Tom.
Alright, okay, so I'm Tom Robitaille and Astrophog on Twitter, and I'm going to talk about multidimensional data exploration with Glue. So for anyone who doesn't know what Glue is a tool for linked and multidimensional data exploration, and you can find out more at glueviz.org. Since the rule of live demos is to not do them, I'm going to show some recordings of, let's see. Okay, so just to give you an idea of what Glue can do, and this is only going to show a small fraction of the functionality. So the idea is, so Glue is this GUI interface where you can have multiple data viewers, you can have different data sets. So this is a catalog data set where we're selecting some points. You see those selection propagate to other viewers. And then this is a separate data set of an image with a histogram of the pixel values. We can select the actual pixel values here and see the selection be highlighted in the viewer. We can also actually create, for example, interactively new components in the data. So for example, for the catalog data, we might want to compute a color. So we can go and take, for example, interactively different components of the catalog. So the 4.5 micron magnitude in this case, and the 24 micron magnitude, we give it a new name, and then we can attach it to a specific data set. And then once we do that, we can then update the histogram on the bottom left here to actually show the distribution of colors. So now we can actually see the sources set very nicely into two different categories. We can go and update the selection to actually select just the points here. We see the selection updates up there. Now, these two data sets are not the same, essentially. I mean, and so we need to actually link them together if we want the selections to propagate. So we can select the array in both catalogs and the declination in both catalogs. But sometimes actually the links aren't so straightforward. You actually have for example, you could have a celestial coordinate transformation. You could actually define any transformation you want. So the idea is Glue is hackable. You can create your own transformations, data viewers, and things like this. Now we've linked the coordinates between the two data sets. We can now highlight the subset of points from this selection onto this viewer. And we can also now select in this viewer both points and essentially pixels from the image. So you can see the selection now propagates to all the viewers. So that's the central, fundamental point of Glue, is to link data sets together, to glue them together. And then you can essentially make selections and see how they propagate. So what we've done recently, this is just very recent work, we've added functionality, 3D functionality. So this is a 3D scatter plot viewer showing earthquake data. So this is the map of the world. This is the mid-Atlantic rift. And then we can select in depth versus magnitude. We can select some points. We see them highlighted in the 3D viewer. So you can actually see these are the earthquakes that happen very deep in the earth, at least in the crust. And then we can see that selection highlighted. We can also go to this histogram of magnitudes. We can update the selection to show just the strongest earthquakes in the world, but not filtering by depth now, just by magnitude. Then we can also select some of the weakest ones that were recorded. This data set is not a uniform data set. You can see that the weakest earthquakes are basically in North America. And that's because they have more sensitive detectors there, and the data set is very heterogeneous. It's a collection of different data sets. So you can actually see, we can zoom in and see that selection highlighted. Okay, so another thing you can do is you don't have to always just use it to show subsets. For 3D exploration, you can also color code the points by, for example, another parameter, for example, depth. So in this case, the red points are the ones that are the deeper. It helps you get a little bit more of a sense of essentially the depth dimension. And you can actually zoom in, recenter the visualization on this region here, and you can see a very nice subduction zone. So in 3D, you can see that the points are essentially forming this kind of essentially plane that's not along the crust of the Earth. You can also use size to encode basically some data. And so there we're encoding the magnitude of the earthquake is proportional to the size of the points. Okay, and then finally we have data volume rendering. So this is actually, we had this kind of traditional slicing of cubes before. and now we actually can have a full three-dimensional visualization here. Again, we can interact with the cube. This is all rendered with OpenGL. You can actually, for spectral cubes, it makes sense that sometimes the third dimension is not actually meant to be seen in the same pixel scale as the other dimensions. We can again make selections in certain plots and see them highlighted. And we've worked also recently. I can't show it yet, but on actually selecting things in the three dimensions and having that propagate to other viewers. Okay, so all the code is on GitHub, and if you would be interested in getting involved with the development, there's a lot of things you can create, or your own custom viewers and things like this, and linkers, very easily without actually have to understand the whole code base. If you're very interested in doing this, then please talk to me. Maybe we can even sprint on it tomorrow at some point. All the code is on GitHub. Please go check it out.
Thank you.